Welcome to Fisher Control's video training program. We hope you find that the information in this course helps you to perform your job more efficiently and with greater understanding. This videotape presentation has been developed in coordination with a corresponding student guide entitled Understanding Loop Controls. Whether you read the entire student guide before watching this tape or read it section by section as you progress through the tape, it is a good idea to follow along with the guide as you view this presentation. This is the second of 5 units dealing with the study of fundamentals of process control. This is an introductory course designed to familiarize you with the rationale, terminology, and techniques involved in the control of various types of industrial processes. As we progress in our study of the fundamentals of process control, it is important to remember that the process itself, as well as its control system, are independent operations. Only when these two elements are brought together to function as a unit can we actually have process control. As you might imagine, the field of process control can become very complex as more and more elements are added to both the process and the control sides of the equation. For starters, however, let's just consider that only 2 types of process control are commonly used. One is called open loop control, and the other, closed loop control. Open loop control simply means that the process is controlled without measuring an actual controlled variable to assure that it is at the desired set point. Usually this term describes various types of manual process control, or some types of variable mode, or automatic manual control. It follows then that closed loop control is usually implemented through the use of process feedback. Here a controlled variable is measured, and that value is then used to generate a control signal that will change the process input in a way that will maintain the process at or near its set point. You can see why closed loop control is normally referred to as automatic control. In this unit of study, we will spend some time becoming familiar with several of the major calculated components of control loops, and we'll learn some guidelines about how to select the proper control loop components to do a certain type of job. We'll also learn some basics about the standard symbols used throughout industry to describe control loops and the various devices that are associated with process control. A process is a system which acts upon inputs to produce specific outputs. There are simple processes which involve only one input and one output, and more complex processes that require multiple inputs and multiple outputs. Specific examples of processes might include a flow tank, a heat exchanger, a chemical reactor, or any other system configuration that requires a controlled, measured output. The variables that influence the status or condition of a process are called inputs. The variables which change as a result of changes in the process inputs are the process outputs. Obviously, if we can identify all the important inputs and outputs that affect a process, it makes it much easier to understand the way the process works. In order to keep the analysis of a process as simple as possible, only the inputs and outputs which can be measured or controlled should be considered as part of the final process control solution. As we have suggested, a control loop can become a very complex system consisting of actuators, transducers, transmitters, relays, and other devices that perform specific control functions. Because so many components are involved in controlling a process, sometimes it is helpful to use the definition of a process provided by the Scientific Apparatus Makers of America, or SAMA. The SAMA definition sets the process apart from its controls. In other words, the process consists of its inputs and outputs, and none of the control instrumentation. Other standards define the process to include its control instrumentation as well. This definition is most often used in describing practical applications. As we discuss the nature of control loops, we need to identify the components involved and discover how the loop responds to change. We do this through conducting a loop response test. In fact, since a change in the process load will bring about a change in the process gain and time constant, it may be necessary to conduct response tests at differing loads. One component that must be evaluated in any control loop is stability. In a closed loop, such as this one, notice that the transmitter is measuring some process variable. The output of the controller goes to a transducer, which feeds an actuator on a control valve, which in turn manipulates the input to the process. The reason that this system is considered a closed loop is because the controller is automatic. Because of this, a change in the set point will cause a corresponding change in the process variable. This value may tend to oscillate or swing back and forth over and under the set point for a while, but ultimately it will settle down at a new constant value. This is referred to as closed loop stability. By switching the controller to the manual position, we change to an open loop system. In this particular case, the valve is manipulated manually. This means that any change in the process as measured by the transmitter will not be acted upon by the controller, but rather by an operator monitoring the variable. For example, a change in set point, as seen here, will cause a corresponding change in the process variable. It may tend to periodically overshoot and then undershoot the set point, bringing about an oscillation. Since it does not tend to settle down, this response is said to characterize open loop instability. Loop stability is based on two factors, loop critical frequency and loop gain. The critical frequency is a loop's natural frequency, or operating cycle. If this frequency is not maintained, the loop will tend to oscillate. Each component in the loop, including the process, has its own gain. Total loop gain is the sum of all the loop components, and if it is too high at the critical frequency, it will also cause the loop to oscillate. Normally, too much loop gain can be remedied by a simple adjustment of the controller. In some cases, however, the loop may not be very responsive, and this can indicate a need to change some of the other loop components in order to achieve stability. For example, in this unstable system, this line represents the set point, which was originally set at 40%. A step change increases the set point to 50%. This resulting curve is the output of the controller to the valve. This line shows the curve of the process variable. If this were a stable system, you would see the process variable move up to the new set point and settle to a new steady state value. What is happening here, however, is that the process variable continues to oscillate. In this particular case, the instability is due to the loop gain being too high at the critical frequency. In order to achieve loop stability and responsiveness, it is important to identify and measure all the lags in the loop, including the process itself. The reason for this is that if the largest, which is to say the slowest, lag is too close in length to the next slowest lag, it will be difficult to tune the loop to achieve stability. In other words, the slowest lag should be dominant or substantially slower than the next slowest lag, and by as wide a separation as possible. This procedure is called dominant time lag stabilization. Simply put, it means that every closed-loop feedback control system is easier to implement and will perform better if there is one dominant time lag in the system. Ideally, this dominant lag would be the process itself. Therefore, all we need to do to achieve dominant time lag stabilization is to select instrumentation that has a response that is much faster than the process. In the accompanying student guide, you'll find several charts of representative types of loop control hardware and their time constants. These are fairly standard throughout the industry and should give you a good idea about how the different devices perform. Transmitter time constants, which are also charted in your student guide, should meet two requirements. First, the transmitter time constant should be at least as fast as the process. Second, the transmitter should not be the dominant lag. Many transmitters have adjustable time constants to allow a predictable range of values. Temperature transmitter time constants are also dependent on the fluid velocity flowing past the sensor element. The greater the velocity, the faster the time constant. You will also find a chart of specific time constants for pneumatic loop components. In these devices, different actuator size is the prime reason for the range of values. As the actuator size increases, the time constant increases. Now that we have some of the major loop components in mind, let's examine how they can be manipulated to troubleshoot an unstable loop to get to the heart of the control problem. The first step, of course, is to perform an open loop test in order to determine the process time constant. Next, you should establish the hardware components of the loop and identify and measure the slowest and second slowest lags in the system. If these two time constants are not separated by at least a factor of 10, you should either slow down the slowest lag or speed up the second slowest lag until this separation has been achieved. In looking at the chart of a fast process, we see that the actuator, I over P, should be slower and the transmitter faster. Conversely, in a slow process, the process should be slower and the actuator faster. The second slowest lag could be made faster by adding a positioner. In a slow temperature loop, if the stable tuning is not responsive enough, the process should be made slower, or the transmitter and sensor should be faster. For pneumatic controls in the slow process, the process should be made relatively slower, which could be achieved by adding a positioner to make the controller and actuator faster. For faster processes using pneumatic controls, the controller and actuator should not be the slowest lags in the loop. This can be achieved by adding an instrument relay or booster, which becomes the dominant lag. Positioners are another loop component that you'll often encounter as you work with control loops. Positioners are traditionally used in many ways: to overcome valve friction, to set valve position in split-ranging applications, to position piston actuators, to provide for a more accurate reading of valve position, and for altering valve characteristics. Positioners can also be used to provide a dynamic effect on loop stability. In general, this works best on slow processes like these shown on the chart. Notice that they are not recommended on fast processes, since they may tend to cause instability. Instead, the addition of an instrument relay is recommended to improve performance on fast processes. If positioners must be used on fast processes, you may need to compensate for them by adding additional lags. Of course, this in turn may require you to detune the controller or otherwise modify the process in order to avoid cycling. Three types of lags that could be added include longer pneumatic transmission lines, which should be kept within a range of 20 to 100 feet of the actuator. Needle restriction valves, which are prone to plugging and are difficult to set. And volume tanks. Volume tanks are a very effective way to add more lag in certain situations. They should not be added in a feedback sensing line, since this would interfere with feedback and result in poor control. The term symbology simply means communication through the use of symbols. Often symbology is used for communication among people within a certain specialty. It will probably come as no surprise to you that the process control industry has its own well-developed symbology, some of which you have already seen demonstrated in this course. In the area that we have been studying, symbology is used to build descriptive diagrams to communicate control strategy. As you'll probably realize, the nice thing about a symbol is that it can communicate a concept without using words, or at least using very few of them. Because of this, symbology is a very valuable tool that is used throughout the world by engineers, system designers, and operators who may not speak the same language, but who understand the same symbols. Diagramming is usually limited to three methods: block diagrams, Instrument Society of America or ISA instrumentation symbols, and identification, and the method of functional diagramming of instrument and control systems of the Scientific Apparatus Makers of America, also referred to as SAMA. Block diagrams provide a general description of a system, minus all the details. They are often used by engineers to describe the inputs, outputs, and summing junctions of a system. There is no industry standard for block diagramming. ISA symbology is oriented toward the description of hardware and is most often used for process and instrument diagramming. SAMA symbols are easily recognizable pictorial representations of various devices and components of control strategy and the relationships between them. SAMA diagrams are used by most manufacturers for diagramming modulating control logic. First, let's look at some basic building blocks of ISA symbology, beginning with the circle. Circles can be used to illustrate a variety of devices and their locations. For example, a plane circle indicates that the device is mounted locally or near the point of interest. Draw a solid line through that circle and you are indicating that the device is mounted in a panel, probably in the operator control panel. If the line through the circle is dashed, this indicates that the device is located on the rear of the panel, probably out of sight of the operator. The dashed line could also indicate that the device is rack-mounted among many other rack-mounted devices. In your student guide, you'll find a list of identification letters and their meanings. Notice that if a particular letter is the first displayed, it is an indicator of a certain measured or initiating variable. Flow, for example. Succeeding letters indicate a readout or a passive or output function, such as an alarm. By interpreting these letter codes, we can pinpoint clearly what type of device a given circle represents. For example, a plane circle, that is one with no lines, containing the letters FC, would indicate a flow controller that is locally mounted. This illustration shows 9 devices which can be identified using our listed identification letters and the 3 types of circles. They are as follows: a locally mounted temperature measuring element, a front panel mounted position indicator, a front panel mounted level indicator controller, a locally mounted temperature transmitter, a front panel mounted differential pressure indicator controller, a rear panel or rack mounted temperature alarm, a locally mounted pressure or vacuum indicator transmitter, a rear panel or rack mounted level element light switch, a front panel mounted flow recorder or printout. As you familiarize yourself with the ISA letter codes in the student guide, you'll probably become aware of the fact that there are often several ways to express the same computing function. The important point to remember is that the symbology elements within a circle are there to communicate to the person reading them that the indicated computation must be performed at that station. As long as that computation is adequately communicated, the choice of symbols is not important. Controllers, transmitters, thermocouples, and other devices communicate with one another and with their indicators and controllers through instrument lines. Some of the ways of illustrating instrument lines and their uses are shown in this chart. For example, 3 hash marks on a solid or dashed line connecting 2 devices indicates an electrical signal between them. Actuators are a good example of devices that are represented by a drawing that depicts the hardware. For instance, here is the symbol for a pneumatic actuator without a positioner. The 2 hash marks on the instrument line would indicate that the actuator is activated by a pneumatic signal from a controller. However, this actuator receives no feedback of the actual position of the device being acted upon. Actuators are very popular devices which are used in many diverse applications. A good understanding of actuator symbology will be important as you continue your study of control loops. Valves, dampers, and louvers are all examples of final control devices. Of course, of these three, valves are probably the most widely used and the most recognizable as to type from their pictorial representation. In this illustration, we show a standard globe valve, a rotary valve, a butterfly valve, and a three-way valve. Again, bear in mind that you'll be seeing a lot of valve representations in control loop diagrams, so you should be very familiar with valve symbology. Control valves and regulators are also easily identified by their pictorial representations. For example, this is a two-way valve set to fail in the open position. Again, bear in mind that you'll be seeing a lot of these in control loop diagrams, so you should be very familiar with them. Control factors that are considered to be primary elements include temperature, pressure, position, and flow. As you can see from the examples in your student guide, the symbols indicating these functional devices are very easy to understand and are very versatile. Here are symbols for a thermowell and a thermocouple, which are almost always used in temperature sensing applications. Here is a level indicator of the most basic float type and another, more sophisticated sonic type level indicator. To show the interaction of primary elements and ISA diagramming symbology, let's look at this diagram in which we have a flow transmitter, a pressure transmitter, and a temperature transmitter inputting data to a rack-mounted flow computer, which is calculating mass flow. The output of the computer is linked internally to a flow indicator controller mounted on the control panel. This controller furnishes an electrical signal which activates the control valve. As technology has advanced and the use of microprocessors has become more widespread, the job of communicating control strategy has become more functionally oriented. The use of ISA symbology alone limited the ability of engineers to communicate accurately through diagrams. To solve this problem, the symbology of the Scientific Apparatus Makers Association has been combined with ISA symbology to provide a more comprehensive diagramming system. SAMA symbols are in many cases the same as ISA symbols, but they are directed more at providing a functional description of the device rather than just a picture of the physical hardware. For example, these SAMA enclosure symbols represent the function of the represented device. A circle in the ISA standard represented only a device of some type and how it was mounted. In SAMA symbology, the circle now indicates a device that is measuring something and/or supplying a readout of the measured value. Automatic signal processing, as indicated by the rectangle, would indicate that the device has an input and will automatically manipulate the data to provide the proper output. The diamond symbol represents manual processing performed at a manual station of some type under operator control. The symbol for a final controller, a trapezoid, shows that the device is being manipulated by the process variable and sometimes furnishes a signal to the final control device. SAMA also provides a number of signal processing symbols which indicate the action programmed into the microprocessor. These are included in your student guide. Familiarization with these will make the functional diagramming of a process much easier to understand. Let's look at some examples of how SAMA symbology works. Here we have a diamond which represents manual signal processing. The letter A indicates that the signal is analog. The rectangle or square represents automatic signal processing, in this case, multiplication. In other words, this is a manually input signal to a microprocessor or analog processor which automatically multiplies the input by some factor. If the multiplication sign in the rectangle is changed to a plus or minus sign, the indication is that we have a manually input signal to a microprocessor which performs a bias function between two valves, for example. Here we see a second diamond parallel to the first, with a T in one and an A in the other. This indicates a manually controlled transfer of a signal. Finally, we have three parallel diamonds which are labeled A, T, and A. Inside the square above is a plus or minus, or biasing symbol. This illustrates that the signal to this microprocessor can be transferred automatically or manually, and that the value of the signal output can be varied manually, as indicated by the feedback signal out of the diamond on the left. Another illustration of the use of SAMA symbology are diagrams describing the set point source for local and remote sources. The first diagram shows a set point which is set manually, and as indicated by the letter delta, is compared to the process variable, which is input from a transmitter. The difference in these two values is sent to the proportional integral, or PI, controller, which computes the desired change. This signal is then transmitted, either manually or automatically, to the device being controlled. It should be noted that the fact that adjacent diamond symbols are touching does not necessarily mean that they are functionally linked. Now let's examine our second illustration, which is for a remote set point. As you can see, this configuration accomplishes the same signal comparison and processing, but this time the new set point signal can only be forwarded automatically. The manual option has been removed. Let's return to our local set point example and expand it a bit. Note that there are thumb wheel settings, probably on a control panel. These are used to manually adjust the set point. Elaborating a little more, let's assume that a process variable indicator has now been added, along with the thumb wheels. We have also included an automatic limiter to control the high and low signal outputs. All these additional components, which provide for tighter process control, are easily represented in our diagram. When more complicated diagramming is required, ISA and SAMA diagramming are often used together in order to provide a complete picture of the hardware and its function. In this example of a three-element feed water control, we see that on the steam flow side, a differential pressure transmitter feeds a signal to an automatic signal processor, which in turn feeds a square root signal to a summing device. On the drum level side, a level transmitter sends a signal to the controller while simultaneously displaying it on a level indicator. The differential signal is acted upon by the controller and is either automatically or manually sent to the summing device. On the feed water flow side, a differential pressure transmitter sends a signal to an automatic signal processor, which feeds the square root output to the controller and simultaneously displays it on the indicator. The PI controller compares the signal inputs and transfers the output either automatically or manually to the feed water control valve. This signal activates an actuator, which opens or closes the valve, depending on the signal sent. In this portion of the unit, you have probably noticed that the clearest diagrams are those that combine ISA and SAMA symbology. As you see more and more diagramming and generate diagrams of your own, you'll undoubtedly find that this combined symbology provides the best means of communication of control logic. So far we have discussed a number of loop components, which will be important to your understanding as you continue your studies in this course. Another important subject, however, is the concept of the different control strategies that tie all the loop components together into a functioning unit. Most control strategies are built around the use of the proportional, integral, derivative, or a PID controller. The three processing modes of this device can be used individually or in combination with other modes, PI, PD, or PID, to provide the proper degree and type of signal processing. Proportional control action deals with the value of a process error as it occurs by comparing the value of the controlled variable to its set point in order to establish the presence and extent of error. The controller then provides a control signal that is computed in a preset proportion to the amount of error. This proportion, which is the output of the controller, divided by its input is also called the proportional gain. If the gain setting provides a signal that does not fully correct for the error, then the amount of remaining error will continue, since the controller cannot tell that it exists. Integral action addresses this problem by providing a repeat of proportional action on the error. The frequency of these repeats is called the reset, and its effect is to make it possible to avoid a continuing error by continually correcting it until it reaches zero. Derivative action is so named because it looks at the current rate of change of the process error to derive what value that error will have at some future time if it continues to change at that rate. Using this projected value, a corrective control signal is produced to cause a change that anticipates and corrects for future errors. The length of time in minutes that the current rate is projected forward is called the derivative, or rate setting. Now that we have mentioned the basics of control actions, let's discuss briefly several of the most common control strategies. Feedback control is the controlling of a process variable through the use of a process error signal. It is by far the most common strategy and is the building block upon which all other strategies are based. However, feedback control can only occur after an error has been generated. Feed-forward control is a strategy that monitors certain measurable and controllable disturbances to the process and transmits changes in their values forward to the controller before their effect has been monitored in the controlled variable. This has the effect in the controller of generating a substitute feedback signal, which produces a corrective action before a measurable error has actually occurred. Cascade control describes a configuration used to control a process that really operates as if it were two processes in series. In this strategy, two feedback loops are used. The set point of the inner loop, which controls the first process, is furnished by the output of the outer loop, which controls the second process. Through the use of the proper controls applied through proper strategies, extremely effective control loops can be designed and, more importantly, implemented in the field.